Welcome to our learning workshop today. We're going to actually be going over alkenes elimination and comparing it to, in some senses, substitution as well. Because these types of things can actually occur under the same conditions, substitution and elimination. It can be kind of tricky to discern which one takes place. So before we begin, how are you at naming of these things? Do you want to take a moment to do any of the naming, or do you want to just skip that part of this?
Let's just skip it. It's something that I can sit and figure out on my own, you know?
Sure.
So
Okay.
that's a practice thing.
No problem. Okay. What about alkene stability?
Yeah, let's go over that.
Okay.
Yeah.
So alkene stability is based upon the number of alkyl groups that are attached to the double bonds. So when determining the stability of an alkene, you want to determine whether or not it's monosubstituted, disubstituted, trisubstituted, or tetrasubstituted. So what that means here is I look at my two double bonded carbons, okay?
Mm-hmm.
That's my point of reference. So I look at how many carbons are those bonded to. So I'm actually going to highlight. So this one has 1, 2, 3, 4. So there are 4 carbons directly bonded to this. Now, why does that stabilize it? Well, that's a good question. Essentially, think of it like this. A double bond between 2 carbon atoms, that hybridization causes a net effect of those carbons that are double bonded having a greater effective electronegativity. So they have greater attraction for electrons. And part of this may be because when you're sharing more pairs of electrons, you have less of your own electrons that are devoted to yourself. You know what I'm saying? Right. You're sharing those electrons the same. And so that's what those bonds are shorter so that they can share. And so those carbons end up grabbing at electrons a little bit more. So to stabilize them, carbons will be able to donate more electron density than, say, a hydrogen, because the hydrogen only has 1 valence electron, right, and whereas carbon has 6. Well, carbon has 4 valence electrons, but 6 total electrons. Mm-hmm. So the inductive effect stabilizes these carbons by allowing electron density to be transferred from these alkyl groups through induction, basically through the single bonds, the sigma bonds. So this in fact, this one is tetrasubstituted because it's bonded to 4 carbons. What about the one next to it? How many carbons is this one bonded to?
It only has the 2 on either side if you don't count the actual molecules themselves.
Yes, because so these are the hydrogens, right?
Yeah.
And so, yeah, this is only going to be disubstituted, has 2 carbons down here. And what about this one?
Trisubstituted.
Trisubstituted. So in order of stability, if we wanted to say from least stable to most stable, this would be 1, the least stable, 2, the second least stable, and 3, the most stable. Or I guess it doesn't really say. I'll just put most here, because one could make an argument that 1 should be the most stable, but we're going to say 3 is the most stable, and 1 is the least. Okay, so that one's pretty straightforward, right?
Yeah.
So finally, something that's straightforward.
Right?
Okay, so no, we'll go ahead and skip this next one then. Now, it says for each of the following elimination reactions, assume a concerted reaction is taking place. and draw the mechanism. Okay. So, in this case, it's only referring to this one reaction.
Right.
Now, normally when we talked about substitution reactions last time, the chlorine is a good leaving group.
Right.
And it's in a tertiary position, so it could leave on its own.
Okay.
Why would it be that the hydroxide would not just wait for the chlorine to leave on its own?
Because don't you have to have nucleophilic attack to start everything?
No.
Okay.
In fact, in the case of a tertiary leaving group, nucleophilic attack cannot start anything because
there's nowhere for it to go.
Yeah, it's too crowded for it to fit in. You
Okay.
have to wait for the leaving group to leave. But OH doesn't wait for the leaving group to leave.
Is it just because you know that it's a concerted reaction?
It is the reason, but yeah, the question is why. And the reason is because hydroxide is too strong of a base to be patient enough to wait for chlorine to leave on its own. So it's going to, instead of waiting for chlorine to leave and then coming in and attacking, and thus giving you substitution, it's just going to go ahead and rip off a hydrogen and cause elimination. Now the hydrogen, it can rip off. So this carbon, the carbon I'm going to mark in blue, the carbon that's attached to the leaving group, this is the alpha carbon, okay?
Yeah.
The carbons that the carbons that are marked in, I guess, reddish orange. I don't know, I'm colorblind.
Beta.
These are beta carbons. And another, because you always go in the order, you know, alpha, beta, gamma, you know what I'm saying? So these are beta carbons. They're one removed from the leaving group. It's the hydrogens on the beta carbons that get removed in elimination. So let's go ahead and show these hydrogens. You know, 1, 2, 3, 1, 2, 3. And then, of course, this one only has 1, right?
Yeah.
Yeah. So the question is, which one of these will the OH remove? And you can see from the product that it's going to end up being which one?
Your central, one of the central beta carbons.
Yeah, the one down here, right?
Yeah.
So this is going to be grabbed, ripped off by the OH. That's going to form this double bond, which is going to kick out this chlorine. And that gives you this.
Yeah, okay.
Now, could it have ripped off one of those hydrogens above?
It could have, but that would have resulted in the loss of that chlorine.
That either one of those above ones would have caused the loss of a chlorine, just like this one.
Why?
So,
it would have just pushed the double bond. Yeah.
Yeah, the double bond would be here or here instead of here. Now, there's two reasons why that. Well, there's really one main reason why that happens to give you this. It prefers to give you this product. Based on what we just went over, what do you think that is?
You have a tertiary beta carbon?
Well, I mean, not necessarily.
Okay.
Because the interesting thing about that, I mean, if we're looking at this from the perspective of this OH ripping off this hydrogen here,
yeah,
that would initially put the negative charge on this tertiary carbon. And tertiary carbanions have the opposite stability pattern of carbocations, which means that tertiary are the least stable.
Okay.
The reason why this is their product is because this is tetrasubstituted.
Oh, so that's how it ends up.
Yeah, this gives you the most stable product. Whereas if I had removed one of these hydrogens up here, it would give me a disubstituted product, which is less preferable.
That makes
Now,
sense.
one thing to note is that you do actually still get some of the disubstituted product. It's just going to be a minor product. It's not going to be the major product.
Okay.
Cool. All right. Now, in the case of the next one, A10, this is the leaving group, or rather, the base is what kind of a base?
Can't water be, strong or weak? It doesn't have to.
It can be an acid or a base, but it can't be strong or weak.
Okay.
It is condemned to be weak.
Okay.
Water is a weakling.
Okay.
So the chlorine, it can't kick out chlorine in any way, shape, or form. It can't rip off a hydrogen and force this to happen. It has to wait for chlorine to leave, to be honest with you. So that means in this case, the first step here is going to be the leaving of the leaving group.
Okay.
And then that's going to give you
Intermediate.
This intermediate. You have positive charge on this tertiary carbocation, or on this, you get positive charge on a tertiary carbocation. And so now actually there's two potential things that can happen here. Once again, here's your alpha carbon. And you also have your beta carbons here with the hydrogens attached to them, which I'll go ahead and draw. Now I'm going into a little bit more detail than these problems are really asking you to, but I want to give you a full picture here. Based on what you've seen, based on what you've already seen in the substitution chapter, what could you expect to happen here? What's one possibility?
I don't know.
You don't know? Yeah, that's okay. Water could potentially act as a nucleophile, right?
Yeah.
Oxygen could come in and form a bond where that positively charged carbocation is. It has two lone pairs of electrons. It's pretty negative itself.
Right.
So it could definitely come in and attack that carbocation. However, what's another thing it could do?
It could come in and get protonated again by a hydrogen.
It could grab one of these hydrogens.
Yeah.
And of course, the one that would be most willing to come off because it would give you the most stable product would be...
Again, that one, yeah.
Yeah, this one. And that gives you this. That gives you this two-step process, which gives you the final product.
Yeah.
Now, the truth of the matter is, under normal circumstances, the substitution reaction would probably be preferred.
Right.
However, if you, you get both substitution and elimination, but the substitution reaction would actually be the preferred one. However, to make this reaction happen, what you would do is you would add heat to it. Additional heat makes the collisions more violent, and it makes it easier to strip off one of those hydrogens, and a little bit more difficult in some ways to get to the carbocation.
Okay.
It also makes the reaction more reversible as well.
Okay.
So there we go. Now, next one, it says predict the major and minor product for each of the following E2 reactions.
What is the name of the reagent?
Oh, the reagent? That'd be
Yeah.
sodium ethoxide,
Okay.
OET. That's shorthand for OCH2 CH3.
Okay.
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 And of course, it's basically a deprotonated alcohol.
Okay.
Negative charge there. It's a very, very strong base.
Okay.
Okay. So in this case, a hydrogen is going to get ripped off.
Mm-hmm.
And first thing we want to do is identify our alpha carbon, which in this case would be which one?
The one with the most substituted carbon.
Actually, the alpha carbon is going to be the one, not the most substituted, but the one with the leaving group attached to it.
Okay.
All right. And then which hydrogen would get ripped off? Before we can do that, before we can decide that, we have to look at what are our beta carbons.
You have 3 beta carbons in various forms of substitution.
So I have one here, right?
Yeah.
One here.
Yep.
And one here. Now,
Yep.
which one is obviously eliminated from, no pun intended, from consideration?
The furthest left.
Yeah, because it has no hydrogens, right?
Yeah.
So then we have this, or this,
Right.
or this, and then what others do we have?
You've got 2 there.
Yeah. So those are our only 2 options, right?
Right.
And which one would be preferable?
Probably the one furthest to the right.
Yeah. There's a little rule that you can remember. Markovnikov and Zaitsev.
Mm-hmm.
Those 2 rules can be summarized by the rich get richer and the poor get poorer.
Mm-hmm.
So the hydrogen, or whichever one of the beta carbons is poorer in hydrogen, that's
Mm-hmm.
the one that's going to lose its hydrogen.
Okay.
So like in this case, you're going to learn more about Markovnikov later on, but in this case, the Zaitsev rule, or the Zaitsev product, there's 2 types of products you can get in this case, the more highly substituted product and the less highly substituted product.
Mm-hmm.
The more highly substituted is the one that's more stable, like this one up here.
Yeah.
So that more highly substituted product is called the Zaitsev product, and it's spelled like Z-A-I-T-S-E-V. Good Russian name, Zaitsev. So, sorry.
No, you're good.
And then so Zaitsev product will be the more highly substituted product. So that will be this one that I'll draw right here. And the Zaitsev product is generally favored over the Hoffman product, except in specific circumstances. And what are those circumstances? Largely, it's if either the base or the substrate is very sterically hindered.
Right.
So in this case, ethoxide, it's maybe a little bulky, but it's not very bulky. So it's not going to be terribly sterically hindered. And so
Right.
you're going to get elimination occurring here. Now, strong bases are also good nucleophiles. So you might be like, well, why doesn't this just come down and attack here and kick out the chlorine? Well, the answer is because it can't really do that, because that chlorine is a tertiary carbon, is on a tertiary carbon, and so it's very sterically hindered.
Okay.
So that's not gonna work real well for it. Instead, it's just gonna go ahead and rip off that one of those beta hydrogens. In this case, the beta hydrogen here. Whoop. Whoop. Just cause those electrons here and kick out the chlorine. Okay, that was kind of terrible, but oh well.
This is good.
So the next one is Turkitoxide, and what that TBOK is potassium terpetoxide. What that really is, and I'm going to show you what it is because it's kind of a beastly substance. So it's a potassium, or rather, it's a carbon with an oxygen and a negative charge. And of course, it's next to a potassium, which is positively charged. But the other thing attached to this carbon is 3 methyl groups. So 3 CH3s. So you got a CH3 here, got a CH3 here, and you got a CH3 here. So this is very bulky. Very bulky. It's hard for this thing to get in anywhere. Okay?
Yeah.
So if this is our alpha carbon here, and then we have our respective beta carbons, which will be all carbons attached to the alpha carbon. This one is gonna, because it's so bulky, it's gonna seek out the hydrogens that are easiest to access. Which ones do you think?
So none of these have anything. They all have the option of 2 or 3 hydrogen. Probably the one adjacent to chlorine.
Yeah. Yeah, and that's because
3 hydrogen.
that's because these 3 hydrogens are furthest away from other groups.
Yeah.
They're easiest to access. Whereas if you look at these 2 hydrogens down here, keep in mind you also have 2 methyl groups sticking out up here.
Right.
And
exactly.
these are going to interfere with approaching these guys. So yeah, you'll get the less highly substituted product, preferably with this, and that would be referred to as the Hoffman elimination. I'm actually going to erase that stuff, and I'm going to put that stuff down here, and I'll put Hoffman over here. But first, I'm going to draw the product. Yay, draw. So 1, 2, 3, 4, 5, 6. Cute. Then 1, 2, 1, 2. Yay. So that is your Hoffman product. I'll type that in.
Cool.
Hoffman. Hoffman. That's the Hoffman product. And over here, we have the ZSEF product. Now, admittedly, even though you would get the ZSEF product here, there's still probably going to be about somewhere between 5 and 10% of the Hoffman product present on that reaction on the left. And likewise on the other side, even though you'll get the dominant product being this Hoffman product, you will also get probably about 20 20-some% or so of the ZCEF product.
Okay.
All right. Now here's where things get interesting. Now, for 18, one of the things you have to realize with regards to these E2 elimination reactions is that there is a way that they have to occur. That it's not just any hydrogen at any point can be ripped off. It's rather the only time that this reaction happens is when the hydrogen that's being ripped off is on the opposite side of the hydrogen that's being ripped off is on the opposite side of the leaving group.
Because strong bases attack from the back. In that reaction.
It's not exactly that. It's more kind of like if you remember our Newman projections. I mean, you're not completely wrong, but if you remember our Newman projections, basically they have to be anti to each other.
Oh yeah, okay.
So in this case, like for example, if I'm looking at this, I mean this carbon obviously has no hydrogens to eliminate, right?
Right.
So that's not going to happen here. So you actually have two hydrogens here. You have this hydrogen that's in front, and you have the hydrogen that's in back. Now the hydrogen in front, I'm going to go ahead and label with blue, and the hydrogen in back, I'm going to go ahead and label with what I think is red.
Okay. Good work.
Okay. So if I take like a mind's eye type view, here's my eye. It's a weird eye. Don't judge. So then I draw my arrow. Woo. Okay. And I'm checking this out, okay?
Yeah, so looking down from one carbon to the second carbon.
Exactly. So here's my front carbon, and the carbon with the bromine is my back carbon.
Mm-hmm.
So I see that from this eye view, I have one group above me and two groups below me.
Right.
If I rotate that around, that one group above me in the front carbon is a benzene ring.
It is.
And I'm going to make it small, unusually so.
Fine.
And then I have two groups down. Now, if I rotate this thing so that the eye corresponds with my eye,
Mm-hmm.
then essentially the hydrogen is going to be on what side? The right or the left?
The right.
Yeah, it's going to be on the right. So the blue hydrogen is going to be on
Right.
the right, and the red hydrogen is going to be on my left.
Mm-hmm.
So then if I look at the back, I know this Newman projection is just awful.
Okay.
The back one, there's an assumed hydrogen here, right?
Mm-hmm.
So looking back on that back card, the thing that's on the bottom is that tert-butyl group.
Yep.
And the thing that's on the right is that hydrogen.
Oh, yes. Okay. Sorry. I turned around in my head for a second.
That's okay. And on the left, you have the bromine. So which bromine gets ripped off, the blue or the red? Sorry, I should have written this as not an R, but as a hydrogen.
Okay.
I don't know what I was thinking.
I was cracking. Well, you kept saying bromine, and I think you just heard yourself say bromine and wrote an R. But, our groups are a thing too, so.
That's true. All right. So
right.
Hydrogen.
So,
So which one gets ripped off? The blue R or blue red? I mean, the blue H or the red H?
The blue H, because
Exactly.
it's surrounded by a methyl group and a hydrogen, and then on the other side you have a methyl group and a bromine.
Yeah, so this one gets ripped off.
Yeah.
Its electrons form a double bond across the other one, from the front carbon to the back carbon, and then this bromine gets kicked off. And here's the interesting thing.
Okay.
The benzene ring, these two guys,
Yeah.
these are both up relative to the other groups, and these guys down here are both down relative to the other groups. So when you write this product, you can write it kind of like this. You can write it, see, I have a C double bond C, and I have a, so I know that the benzene group, benzene and a hydrogen are together here, and the benzene is up. Okay.
Okay.
So I have this benzene group up. Oh wait, whoops. Sorry.
Sure.
We're gonna just pretend it's right.
That's the molecule.
And then the black hydrogen and the back carbon is also up. The red, or the tert-butyl group, is down on the same as that black hydrogen. And the red hydrogen is also down on the same carbon as the benzene ring. Can you see how that works? What the?
Yeah.
There you go. So that's one way to write this product.
Okay. Convert it to a Newman and then convert it back into a regular line angle.
And you can see in this case, the transformation is given. Now, what's to prevent this from rotating around?
Would you have steric issues between the bromine and the hydrogen? If it rotates along that bond, then that giant
the tert-butyl group would conflict with the benzene ring, right?
Exactly.
To some degree, but this actually can still happen, even though there is steric. But you're right, most of the time it's going to be in this position. It says identify the major and minor products. Okay. So in this case, the major product is definitely going to be this guy here. But the minor product would be is if this thing rotates around, there is another hydrogen. Just like in the Newman projection, I can rotate the front around, right?
Yeah.
And if I rotated this around and I put this here and the red hydrogen here and the blue hydrogen up here, then the bromine and the red hydrogen would be opposite to each other and they would eliminate, and that could give you the cis alkene.
Okay. Yeah.
Does that make sense?
Yeah.
Okay. This is going to be major. Okay. So now I am going to erase this symbol of my shame right here. And we're going to go ahead and take a look at B. Sound good?
Yeah.
Okay. 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 So if we look at the next one, the interesting thing about this one is you'll notice that while I still have the bromine group in the same position,
right,
and there's a hydrogen next to it,
you have a
down here I have a methyl group.
Yeah.
Which means how many hydrogens do I have?
You said the one.
I only have the one beta hydrogen, right?
Yeah.
Which means you're only going to get one product. Now here's the cool thing.
Okay.
Here's a shortcut you can do. remember how I showed you that it has to be opposite? And notice how it was the blue one
Right.
that ended up getting eliminated. So notice the blue one's wedged and the bromine is dashed.
Right.
That means that they would be effectively opposite to each other.
Right.
Now in this case, the bromine is dashed and the hydrogen here is dashed.
Mm-hmm.
They're not opposite, which means for this to react, first this thing has to rotate up. Has to rotate up so that the tert-butyl group is up and the bromine is wedged in front.
Okay.
So if I was to go ahead and once again draw one of my creepy eyes.
Very nice.
And it's looking right there. Creepy eye says, I have a benzene ring. Theme music included.
Once you're good at something.
I know. And then we have the CH3 on the right. And we have the hydrogen on the left.
Mm-hmm.
And in the back carbon, you have the bromine on the left.
Yep.
And you have the hydrogen on the right.
Yep. The tert-butyl down.
And then, of course, down the two. Yep, exactly. Now that bromine, that hydrogen here can't be the one that's eliminated. It's on the same carbon as the bromine. I have to have a beta hydrogen be eliminated. So it has to be this one. So I can rotate these around. Rotate these guys around, and I can go, whoop. And then I can go, do. And then I can go, like, yeah, let's come down here. And I make a clover. So then I will rewrite it as the benzene ring is now down here. The hydrogen is here, and the CH3 is up top. But in the back, I haven't changed anything. I only rotated the front groups, which means there's going to be a bromine. And this down here is going to be tert-butyl.
Mm-hmm.
And this is a hydrogen still. So now this hydrogen can be eliminated. And one of the things you'll notice is that this hydrogen and the bromine are opposite, called anti-coplanar. So
Yep.
they're in the same plane, but they're opposite to each other. They cancel out. You'll notice that the larger groups here, the larger groups are going to be on the same side.
Right.
Smaller groups are going to be on the same side. So this would actually end up being a Z. And Z corresponds to, in some ways, you can think of it kind of like cis.
Okay.
And E corresponds to trans in a certain sense.
Okay.
Strictly speaking, there's a specific meaning. Cis and trans have a very specific meaning, but E and Z are less specific. It just means that the higher priority groups are always in the same position or in the same direction. That would be cis on higher priority groups, or rather E and Z. Higher priority groups in the same direction would be Z. If they're in opposite directions, it would be E.
Okay.
So in this case, we're going to get the Z product, which would be C double bond C, and I'll make this one my front carbon. It has the double bond benzene ring. And I'll just do like a little loop inside for the benzene ring.
Yeah.
That didn't look like a loop. It looked pretty awful.
The other thing didn't look like lines either, so.
Hey, you know what? I'm just Just gonna say, yeah, keep your thoughts to yourself.
Drawing on a computer doesn't make it much easier.
No, I'm just kidding. You're all good.
Like that little
No,
chicken
Chris,
foot you've got in the right corner there.
No, anyway, so yeah, so there you go. So this will be your only product. You're not going to have a minor product. This will be your only product, your
Okay.
Z product. All right. And of course, in this one, you'll notice that the hydrogen is a wedge.
Mm-hmm.
So in this case, this is opposite of the bromine. It can automatically cancel out. You don't even need to do the Newman projection. You can actually just leave it just the way it is and draw the double bond. How cool is that?
Okay. I feel like I'm going to try too hard on the test there.
But no, isn't that cool? Like, if one's wedged, one's dashed, you can just cross them out, and then bam, there you go. And honestly, even with this, if I see that they're on the same side, that just means you have to rotate it around. So basically, just turn this from going down to have it going up.
Okay.
Tributyle. And then draw the double bond, and you're cool.
Okay, it's doable.
Yeah. That makes it a little bit easier.
Okay. So those are
all right. So, and this is a cool one. This one here is a cool example of being aware of that anticoplanar geometry and what type of things you need to look for. Like, because if this is wedged, that means your hydrogen over here is dashed, right?
Mm-hmm.
Whereas if this is wedged over here, that means, hydrogen over here is dashed. Hydrogen on the other side is wedged. Now, which one is opposite to the bromine?
Hydrogen.
Yeah, which hydrogen? The one on the left or the one on the right?
On the right, sorry.
Yeah. Which one is opposite to the hydrogen? The hydrogen.
The hydrogen.
Don't you know which one? Come on.
No.
All right. So there you go. But yeah, so that means the double bond would basically come here. The bromine and this hydrogen would be gone.
Okay.
And one thing to keep in mind is, I'm going to draw this very slowly and nicely and neatly. I know it's kind of nice, but this is flattened. This is flattened.
Okay.
Why?
Why
does this no longer have a wedge or a dash?
Because with that double bond, you end up being planar, right?
Yeah. Mm-hmm. It's sp2 hybridized because of the double bond that carbon is, and so it ends up being planar, which means there's no wedge or dash. It's all flat.
Okay.
And then don't forget here, when you get the big bulky base, you're going to get what type of elimination?
The mean kind.
The what?
I don't know.
So, because keep in mind, like with these two guys, in this case, you had two choices, although actually one of them wasn't really a choice. This just doesn't happen. Over here, though, you do have two choices because you have a dash hydrogen here.
Mm-hmm.
And then, of course, you have a wedge and a dash hydrogen here. Now, the wedge in a ring, it's locked into position, so it can't rotate around. So this wedge will never be able to eliminate with that bromine.
Okay.
But over here, this wedge, this dash hydrogen could eliminate. So you have two dash hydrogens that could eliminate. With sodium ethox, yes?
Wait, how come the wedge one is locked and the dash one isn't?
Well, they're both locked in their respective positions. But, so in other words, the wedge one is locked into being always on the same side as bromine.
Right. Okay.
Whereas the dash one is locked as to always being on opposite side of the bromine.
Okay. Yeah.
So that it's, and now It's a little bit more complicated than that because I mean, it can show you the chair conformation.
Yeah.
Only one of the chair conformations is actually going to allow only one of the chair conformations would allow it to react. The
Yeah.
other one would not. However, there's only one of the chair conformations would allow it to react for each of those dashed hydrogens. So
you're flipping, right?
yeah.
Okay.
So which one would be preferable? The wedge one will never react with the bromine. It will never get eliminated.
Right.
The dashed ones can't. So which one of these dashed ones is going to be preferred?
The far left side because it's not getting any hindrance from the methyl group.
Actually, no.
Why? What? Why?
So sodium ethoxide is not sufficiently bulky. And if you if you get the double bond on this side, it'll actually make a more highly substituted product. So the two products you could get would basically be a double bond over here and a wedge, right?
Yeah.
Well, that would only be a di-substituted. The other product you could get would have the double bond over here, and it would be a tri-substituted. Tri-substituted alkene is more stable than a di-substituted alkene. And so this one over here would be the major.
Gross. Okay.
Gross.
I don't know. It seems really messy.
It is messy. Much more than you realize. So here's the deal. If, however, you have a bulky base like this, which one would be preferred?
That left side one.
Yeah, the left side one, because with that big bulky base, it's going to be way too hard for it to get in on this tertiary hydrogen. It's going to have to go for the secondary dashed hydrogen over here, the one that's less highly substituted. It'll be easier for it to grab it. And therefore, your major products and minor product would be flipped.
Okay. That makes a little more sense, I guess.
Mm-hmm. So yeah, there's lots to consider. So the minor product would be okay. And this would be major for this guy. Okay, cool. So those are kind of some things to watch for. Next. Also, keep in mind stereochemical considerations.
Right.
This actually has a chiral center here. This is going to be either R or S, whereas the other product actually has no chiral center. It's simply going to be 1-methyl cyclohexene.
Okay.
All right. Identify the major and minor products of each of the following E1 elimination reactions. Now, one thing to watch for with an E1 elimination reaction is that you can have carbocation rearrangement. So you can have carbocation rearrangement. Although, what do I want to say about that?
Yeah.
None of these cases actually, anytime you have E1 or SN1, you can have carbocation rearrangement. So you do want to watch for it. But in this case, none of that, you will not have to worry about it for this particular problem.
Okay.
Because you'll notice that the carbon with the leaving group, or at least the prospective leaving group, is always, it's tertiary. With one exception. This is actually a special consideration. It's actually it's not tertiary, but it actually is just as stable, if not more so. It's actually called a benzylic.
Okay. Oh, yeah, that's right.
Because yeah, if this water leaves, then you have a positive charge here, and then this double bond can form here, and then that positive charge can be cycled throughout the ring in several different positions and
Okay.
it can be delocalized. Okay. So this mechanism is called acid catalyzed dehydration of an alcohol.
Mm-hmm.
It's a very common method for making alkenes. Use concentrated H2SO4. This is a reversible reaction, but with concentrated H2SO4, it's going to be heavily pushed
Really got
forward.
tempted, yeah.
Yeah, and you're also going to add a lot of heat to make it happen. So this is protonated, and after it gets protonated, then it's going to leave on its own.
Mm-hmm.
And then what little water might be in the thing is going to actually end up ripping off a hydrogen here and causing elimination to occur.
Friendly.
So once again, we're looking at, and this is one of the key points of this particular mechanism, we're looking at beta hydrogens to be eliminated. So which beta position will I take a hydrogen from?
Probably one of the ones on the right.
Yeah, it's going to be one of these guys, right?
Yeah.
Because that's going to give you a more highly substituted.
Exactly.
Remember, the rich get richer, right?
Right.
So that's self-elimination. Rich get richer. The only time the poor get richer, or rather, the rich get poorer, is when you have a big bulky base. Yeah. So it's just going to be one of these guys over here. That's going to get ripped off. Electrons are going to come here and kick out what will be a water after it gets protonated by the acid.
Oh, okay.
And that's going to give you double bond. And then doop, doop. And same thing with this guy, except this one is ethanol and heat.
Mm-hmm.
Now, with this one, with the one above, sulfate is kind of a terrible nucleophile. It's not really going to come in and attack. It's just not a good nucleophile. But ethanol is a poor nucleophile, but it's good enough that it would actually come in on an E1 mechanism like this. The thing that keeps it from being a major product is the adding of heat here.
Okay.
So that is important because you're going to actually have to distinguish between whether or not it's an SN1 or an E1 product that's going to be the major product. And the key difference between the two is if you want the E1 to be the major product, you add heat. Otherwise, you'll get SN1.
Okay.
And this one, once again, your double bond is going to be. Now, you can still get minor products because any one of those beta hydrogens can be abstracted, can be removed. So you'll still get some minor products, but this would be the major. These are the major products.
Okay.
Now, you said you have to leave at 4, correct?
Yeah.
Okay. Before you go, I want to show you one really cool thing.
Cool.
It is my SN1 under concept reviews. There's the SN1, SN1, SN2, or substitution versus elimination flow chart.
Okay, yeah.
So this is like my magnum opus. Not exactly, but it's still pretty cool.
Oh, shoot.
Yeah. So like,
that's cool.
Awesome. Basically,
yeah.
It gives you a series of questions you can ask yourself to guide you through your thinking whether or not you'll get an SN1, SN2, E1, or E2 type of reaction happening. So is there a good leaving group, or can you make it a good leaving group? If the answer is no, no reaction. If the answer is yes, where's the leaving group located? Primary, secondary, tertiary. Then you have to ask yourself, is a strong base present? If there is a strong base present on a primary leaving group, if the base is a good nucleophile. If it's not a good nucleophile, you only get elimination. But if it is a good nucleophile, you have to ask if it's sterically hindered.
Okay.
If it is sterically hindered, you'll get E2. If it's not sterically hindered, then you'll actually get SN2 as your major product.
Nice.
And E2 will be your minor product.
Yeah.
So it takes into account all these different things. And notice that like with SN1 and E1, is heat added is the last question.
Right. Yeah.
So
you'll get either. It just depends.
Mm-hmm. And it does a good job of summarizing the good leaving groups.
Yeah, that's nice.
And the good nucleophiles.
Yeah.
Bad nucleophiles, strong bases, and strong bases that are bad nucleophiles, strong bases that are good nucleophiles. So,
You know.
Yeah.
If you have to lean on a magnum opus, at least it's color coded.
It is color coded. All shiny and beautiful.
Yeah.
You can see it. Like I'm sharing it properly.
Yeah, totally.
Oh, cool. Okay, I wasn't sure if it would show it because I switched over from the one to the other. But anyway, yes, that's awesome. Well, thank you so much for coming, and I hope that was helpful.